This is lesson 2.3, electron arrangement. So think back to last year. What was the purpose of the flame test and how does it work? So remember the flame test can be used to identify atoms or elements because they give a characteristic color in a flame. And remember that when electrons absorb energy, they jump up energy levels and become excited. And then when they lose that energy and fall back down to the ground state, they emit it in the form of light, because remember that energy cannot be created nor destroyed. So think back to the electromagnetic spectrum. Remember that electromagnetic waves can be distinguished by their wavelengths and their frequencies. And remember, frequency is the number of waves that pass a specific point in 1 second. So c, which is the speed of light, is equal to the frequency times the wavelength of light. So if you know one of these, either the frequency or the wavelength, you can find the other because c is a constant. And shown below is the electromagnetic spectrum. Remember, the longer wavelength is red, like red skins, and then purple, remember, is like ravens, super excited, short wavelength, woo, go ravens. So remember, frequency is the inverse, so the longer the wavelength, right, the larger the wavelength, the lower the frequency, and the shorter the wavelength, the higher the frequency. So line spectra is something new. There's two types of line spectra you need to be familiar with. The first is absorbance spectra, or absorption spectra. Absorption spectra is a line spectra that's created when some colors of light are missing from a continuous spectrum. So here's an example down here of an absorption spectrum. It's the bottom one. And you can see that all of these wavelengths of light are present from the spectrum. However, you're missing just these few lines, okay? And this is created when a gas has white light pass through it. And now it changes based on the identity of the gas. Now, the emission spectra can be achieved when you put high voltage through a gas. So the colors in the emission spectrum are those that are missing from the absorption spectrum. So you can see that in hydrogen, the bottom is the absorption, and where those black lines are, there are now colored lines, and everything else is black. And from emission spectra, you can identify elements because they all have their own distinct emission spectrum. So if this is what you see, you know that you must have hydrogen. It's like a barcode. So remember the Bohr model, remember excited state and ground state electrons, and think back to photons. So a photon is a packet of energy, and one photon is released for each electron in transition. And the energy of this photon is proportional to the frequency of the radiation. So you can determine the energy of the electron by this formula. The change in energy of that electron is equal to h, which is Planck's constant, it's in your data booklet, times the frequency. And electrons can only change energy in certain ways because they can only jump between certain energy levels. So that energy is quantized, meaning a specific amount. Finally, let's talk about the hydrogen spectrum. So again, hydrogen has this distinctive emission spectrum, and the reason that it has this distinctive emission spectrum is because the electrons in hydrogen are always jumping from higher energies to lower energy levels. So let's look at this picture right here, which is really the same as a circular picture for the hydrogen atom. And if an electron falls from any energy level, 2, 3, 4, 5, 6, 7, all the way down to the first energy level, we say that this is part of the Lyman series. Okay? And the Lyman series emits ultraviolet, or UV light, which we cannot see. If an electron in the hydrogen atom is falling from energy levels 3, 4, 5, 6, or 7 to the second energy level, this is part of the Balmer series. And the Balmer series is visible. So these are all the different colors of light corresponding to the energy, the frequency, the wavelength of those transitions. The last one you need to know is the Paschen series, which is any of these energy levels 4, 5, 6, or 7 falling to the third energy level. And the Paschen series is infrared light, so again you can't see them. Now, if you were to completely pull an electron off, remember that's called the ionization energy, the energy required to remove an electron from the ground state of an atom in a mole of gaseous atoms. And you do have to say in a mole of gaseous atoms for IB to give you full credit.